Hi, this is Dr. Bay, and here's Bugsy, and today we're going to go over epoxide ring opening mechanisms, so stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Epoxides have significant ring strain and tend to open up, which would alleviate their ring strain. To go from an epoxide to an alcohol, a nucleophile can attack a carbon atom that's part of the epoxide, followed by the carbon-oxygen bond breaking to form a new lone pair on the oxygen atom. Then the O- can get protonated by water to form an alcohol. Here's a list of common nucleophiles that can participate in a ring opening reaction of an epoxide, and they tend to be strong nucleophiles. The mechanism of a ring opening reaction depends on if the reaction is under basic/neutral conditions or if it's under acidic conditions. So let's go over both cases. Under basic/neutral conditions, the first step is that a nucleophile will backside attack the least substituted carbon of the epoxide if it is an asymmetrical epoxide like the one shown here. The left side of the epoxide is less substituted since this carbon atom is bonded to two H's, whereas the right side or the more substituted side of the epoxide is bonded to two methyl groups. When the nucleophile attacks, it opens up the ring and the carbon-oxygen bond breaks to form a lone pair on the oxygen atom. In the second step of the mechanism, the alkoxide ion gets protonated by water or any other protic solvent. In this reaction, the epoxide is first reacting with sodium ethoxide and then second with water to form the following secondary alcohol product. The mechanism begins with the ethoxide nucleophile first attacking the less substituted side, and then the epoxide opens up. Then the O- gets protonated by water to form the product. Now, under acidic conditions, the first step of the mechanism is actually to protonate the epoxide with an acid. One of the lone pairs on oxygen grabs a hydrogen atom from the acid, and the bond forms a new lone pair on the halogen. Then in the second step, the halogen acts as a nucleophile and attacks the more substituted position of the epoxide, and the epoxide then opens up to form the product. In this reaction, this epoxide is reacting with HBr to form the following primary alcohol product. The mechanism starts with the epoxide oxygen getting protonated and HBr breaking to form a new lone pair on bromine. Then in the second step, Br- acts as a nucleophile and attacks the more substituted carbon, and then the epoxide opens up, which results in the alcohol product. Now notice that the methyl group is now on a dashed bond, which is opposite of what it started on in the reactant. The reason for this is when your nucleophile is attacking a chiral center, there will be an inversion of stereochemistry because the reaction is technically an SN2 reaction. If this is a bit confusing, let's go over a few examples where stereochemistry changes. So you want to pay attention to the stereochemistry of any epoxide ring opening for both types of conditions. In this example, we're going to draw the mechanism for the following reaction in order to explain the observed stereochemistry in the product. This epoxide is first reacting with NaCN and then with water to form a tertiary alcohol. Since it is reacting under neutral conditions, we're going to follow that specific mechanism. So recall that the first step under basic or neutral conditions is that our nucleophile, in this case Cn-, will attack the less substituted carbon of the epoxide. and then the epoxide will open up. Notice that the epoxide contains wedged bonds. This means that when the nitrile nucleophile attaches, it will attach as the opposite bond type of the epoxide, which would in this case be a dashed bond. Then in the second step, the alkoxide ion will get protonated by water to then form the product. But sometimes the wedges and dashes aren't directly connected to the epoxide oxygen atom, but are shown rather as substituents. In this example, this epoxide is reacting with HCl to form the following secondary alcohol. Since it is reacting under acidic conditions, we're going to follow that specific mechanism. The first step is that the epoxide oxygen atom will get protonated by HCl. Then in the second step, Cl- will attack the more substituted side of the epoxide. Since it is attacking a chiral center, we have to invert its stereochemistry. So to do this, we're going to switch the positions of the wedged tert-butyl group with the dashed ethyl group. So notice that the two in-plane bonds, which includes the hydroxyl group and the chloro group, are also anti to one another, where they are pointing in opposite directions. And then with that, our secondary alcohol product is formed. So in summary, because epoxides have significant ring strain, they tend to undergo ring opening reactions. The mechanism of the ring opening depends on whether it is reacting under basic/neutral conditions or under acidic conditions.
Organic.